I would like to introduce today's speaker. Timothy Nelson is an associate principal with Degenkolb Engineers in San Francisco, where he leads the firm's construction engineering working group. During Tim's 13-year career, he has held engineering and management roles on over 70 construction engineering projects, providing designs for steel erection engineering, building underpinning, and excavation support. Tim is a licensed structural engineer in California and Washington and sits on the committee for the AISC 37 design loads on structures during construction standard. Tim, thank you for being here, and I'll now hand it off to you.
Thank you, Nate, and good afternoon / good morning to everyone listening in today. Thank you very much, Nate, for that nice introduction, and to all of you for carving some time out of your day to hear about what I think is a pretty interesting topic. Happy to be here today. I'm also pleased to be part of this series. I think folks who have joined the prior two talks by Tim and Ben, I think, have been treated to some really great insight on those fronts, and I hope to build on that and offer some input today as it relates to erection engineering for high-rise structures. Before we get into the content of the presentation, I did want to make some acknowledgements, both inside and outside my firm. Wanted to thank some of my colleagues at Degenkolb. Alan Roberts, he's a project engineer and SE in our San Francisco office. We've been working closely together for almost 10 years now on construction engineering projects, and he's been right there with me on the projects that I'm going to be talking to you about today, and also helped put together some of the content for this presentation. Really appreciate his input and contributions. Also, Jim Malley and Andrew Scott, both principals in our San Francisco office as well, for their mentorship and leadership. And also my colleague Rainbow Lynn, a designer in our San Francisco office, who has also been assisting and provided some additional content for the presentation as well. Also wanted to thank some of our partners in the industry. The Herrick Corporation, a fabricator erector out here on the West Coast, has been a fantastic partner. We've done a number of projects with them, and the majority of the projects we're referencing today have been with Herrick. We've really appreciated the opportunity that they've afforded us to participate on some of these really interesting and complex projects, and they were kind enough to provide some input on the content that you'll see in this presentation today. The same goes for Pat Hassett and his team at Hassett Engineering out of Castro Valley, California. We've collaborated with Pat on a number of projects and really value the input and experience that he has brought to those projects and the input that he's provided on today's presentation as well. I did want to note that what you hear today is any opinions expressed are coming from me. And if I do end up sharing any opinions that are from these folks, I will certainly indicate that. But it's opinions from myself on behalf of Degenkolb Engineers. One other quick note that I wanted to make is that some of you who may have attended the Steel Conference presentation that I gave, you're going to see some similar contents in parts of the presentation today. But the nice thing about this webinar is that it is longer and has allowed us to build in some additional content and expound on some of the things that we did discuss during the Steel Conference presentation. So there is more that you will be seeing here today, I think, beyond what was shared during that presentation several months ago. So to kind of set the stage, let's talk about some of the observations that we have made in recent years as it relates to erection of steel high-rise structures. And I want to highlight that we're talking about structures that are primarily steel, or in many cases all steel as far as their superstructure is concerned. So there's certainly instances out there where towers are going with no concrete core, kind of foregoing that traditional backbone that you see in a lot of high-rise structures and have for many decades. That introduces some interesting additional erection challenges, which we'll talk about today. Somewhat tied to that, also separate, is the notion of delayed lateral systems. As you're seeing buildings going to these mega braced systems that involve braces that go multiple stories and aren't really truly in service until they get to their top panel point, you're finding larger and higher amounts of erection that need to go up prior to a true lateral system being in place, which obviously creates some stability concerns. Tied to that is the desire to just go higher, faster. I know many of you have heard about the speed core system that has been getting more attention as of late, and kind of decoupling your erection from the concrete and allowing for steel to go up in a much faster cadence, again, can lead to some interesting stability questions and concerns that need a real direct look. Tower crane demands, obviously you're going to need a tower crane or a climber crane for building these structures, and the demands on those can get pretty sizable, especially as they get taller, and the question of where do you send those loads in a partially completed structure can introduce some interesting considerations. We're seeing more variation in the aspect ratios of these buildings, the plan shapes, the irregularities, the added complexity of the lateral systems being used, and that also adds considerations as it relates to the sequence of how you put the building together. Those different aspect ratios, the slenderness, some of these taller, more slender buildings can have some interesting behavior as they go up. And as we get into this complexity, we are seeing that there's a lot more gray area in terms of what is really on the SEOR's plate versus what falls to the erector. That is leading, in our opinion, to a more deliberate shift of certain responsibilities from the SEOR to the erector and in turn their engineer, which again underscores the importance of keeping some of these topics today in mind. So that sets the table for today's presentation. The presentation is organized into 5 distinct sections. So I'll be talking about wind and seismic demands during construction. We'll dig into some of the issues related to the complexity of building buildings like these and how that relates to satisfying erection tolerances as you go up. We'll talk about some of the issues related to those delayed lateral systems and how you push height limits in a safe and effective manner. We'll talk a little bit about erection aids and lifting lugs, not as an exciting of a topic, but there are certainly some things that we think about when we're lifting and setting heavy elements hundreds of feet in the air, especially in tight urban settings. And then we'll finish off with some interesting examples of how we've dealt with tower cranes in the past. So our first topic, demands during construction. You've already heard, if you've attended the prior 2 presentations, some references to the AISC Code of Standard Practice. I wanted to just reiterate what I believe Ben talked about last week and what it actually calls for in terms of considerations of demand. So you can see this out of Section 7.10.3 of the Code of Standard Practice and the highlighted text. And I'll just read a bit of it here. That temporary support shall be sufficient to secure the bare structural steel framing or any portion thereof against loads that are likely to be encountered during erection, including those due to wind and those that result from erection operations. And then separately in the orange highlight, the Code of Standard Practice does note that you need not consider loads during erection that are unpredictable, and it includes hurricane, tornado, earthquake, explosion, collision as examples. So the point for highlighting here today is that, of course, wind is an important consideration, but even though earthquake is not required to be considered, certainly here in earthquake country and in other parts of the country, there may be instances where it is appropriate to consider earthquake, and we certainly do in our practice, especially for buildings on the West Coast. So we're going to dig in a little deeper on both wind and seismic demands today. So we wanted to talk about wind first. And the analogy that we typically use when we're evaluating wind loads on a structure is the truss tower analogy that's referenced in AISC E7, recognizing that for a large portion of erection, the tower is not clad. And it's an interesting consideration. It's very easy to say that a partially completed building would not be subjected to the same degree of wind demands that it's designed for in the permanent sense, but that isn't always true. When you're looking at a truss tower analogy, you're going to be applying your wind loads to exposed surfaces, beams, columns, braces, anything else that may want to pick up wind during the time when it does not have cladding on it. And as you'll see, that can add up. We typically do leverage the reduced wind velocity provisions from AISC 37, which you heard about in Ben's presentation last week. That does allow you to take a reduction, recognizing that your construction project is only over a shortened duration as compared to the design life of a building. And it does allow for some reductions due to shielding, recognizing that a column several bays into the building floor plate is not going to see the same degree of wind load that a column at the perimeter might see. But even with all that, it's definitely possible that significant loads could be seen, especially with these all steel structures. Elements tend to be heavier. You're seeing the advent of box columns, sometimes filled with concrete. These are columns with large surface areas that can take up a lot of wind loads. And then, of course, bidirectional effects. If your wind resultant is on a diagonal, you may lose some of the benefit of shielding of columns stacked in a row because they're all kind of offset from each other when you're looking at a projection of the building from the diagonal. So the wind loads can add up, and it's important to stress that. I won't dive into this too much, but with the truss tower analogy, just wanted to quickly review the general process for developing those wind loads. And this is based off of AISC 710. I did that just because that is currently the standard that's referenced by AISC 3714. Obviously things do change as you go from one standard revision to the next, but the general intent is still there. You're going to determine your wind velocity QZ per the equations in AISC 710 shown here on the top right. You're then going to take a reduction in your wind velocity per the provisions in AISC 3714, section 6.2.1, based on your construction period, and it's tabulated there. The different reduction factors you can apply to your velocity V. Important to note that is applied before you square the V term. So the reduction of 0.75 squared can add up to a pretty reasonable reduction. I should note a little side commentary that there is a revision process for AISC 3714 underway, preliminarily targeting 2024 to release, and the wind provisions are one thing that are going to be looked at pretty extensively because I think there's more data to float into this information as we build out the next version of the standard. Once you take your reduction in velocity, you're going to and get your total QZ, you're going to apply the load using equation 29.5-1 of AISC 710, which is going to, in essence, take your wind pressure and apply it to the exposed surface areas. And if there is an opportunity to take a shielding reduction, AISC 37, section 6.2.2 gives you some provisions for how to do that. The shielding is a very interesting topic. It's certainly can be argued, and I know instances of folks who have actually done measurements within a building to actually try to quantify the reduction. Shielding can play a role. As you get into that building, not only the stacking of elements from one bay to the next can block wind loads, but also the presence of a metal deck diaphragm can also change the dynamics of the wind, and in some ways can reduce the wind quite a bit. The challenge is that the standards out there, as you would expect, are probably taking a conservative approach to those reductions, given the lack of a lot of research on structures during construction, or these truss tower type structures. But that said, there's a number of standards out there which you could reference, and I'd like to share some of them today. And we'll go through each of these and do a little case study of computing shielding reductions. For the case study, here's what we'll be talking about. So kind of a generic example building. We'll be talking about an all-steel high-rise, approximately 60 stories tall, with story heights of 13 to 15 feet. And, for the purposes of this discussion, we're just thinking of it in terms of in fully unclad condition. I know that cladding does start chasing the erection. Typically you're erecting, and then concrete's following, maybe 8 to 10 floors behind, and then cladding perhaps another 10 to 12 floors behind that. But we're just going to take that out of the equation and just think about a fully unclad condition for the time being. The references we're going to talk about are AISC 3714. We'll talk about AISC Design Guide 10 briefly. You heard about that a bit last week. We're going to look also at the standard AISC wind loads for petrochemical and other industrial facilities. There's also an Australian New Zealand standard, 1170.2, and then also some language from the textbook by Shapiro and Shapiro from 2011. The case study will be looking at the floor plate that you see on the right. We're looking at a building that is, has got a pretty extended aspect ratio of about 250 feet in plan left-right, and about 80 feet in plan up-down on the screen. So I won't belabor the AISC 3714 too much here, but the provisions are in section 6.2.2. They're simple to apply, but they also offer a relatively limited benefit of shielding. Highlighted text there is saying that the first 3 rows of elements along the direction parallel to the wind shall not be reduced, but then you can reduce any subsequent rows beyond that by 15%. So the notion of the thinking that you've got a number of rows of beams, and once you get farther into the building, you can take a slight reduction on the wind loads once you get past that 3rd row. But keeping all that in mind, in just a sec while I take a quick sip of water. If you've got a deep floor plate, you can add up your areas to the point where you've kind of exceeded the surface area you would have for just a cladded bay. And you could get a larger wind area than the clad structure. Design Guide 10, which is the low-rise standard. I should note that obviously in the title it's for low-rise structures, and we recognize that and keep that in mind. We do still use this as a reference when determining shielding in conjunction with these other standards, because we believe that it's a coherent document with good justifiable backing to it. And we don't rely on it on its own, but we like putting it in the mix with our other standard considerations, even for high-rise structures, which is in an opinion, and there's some judgment associated with that, of course, but I wanted to make that point. It digs into a more detailed evaluation of shielding, and it's not just thinking about it in terms of what rows you can take reductions on, but actually thinking about the solidity of the entire frame. Looking at it kind of in both the plan and elevation standpoint. And it breaks it down into a more detailed table that you can pick values off of, and can, in certain situations, give you a larger shielding benefit than AISC 3714. The wind loads for petrochemical and other industrial facilities standard, it takes a similar approach to Design Guide 10. The interesting thing about this standard is that it brings solid flooring into the equation as well, which is something that not every standard does and is recognized as something that can contribute to shielding. But again, it does make the point that you could see wind loads that exceed those of the clad structure, and that's something that really needs to be considered through every step of this. The Australian and New Zealand code, ASNZS 1170.2, has similarities to the ASCE petrochemical standard. Again, it's talking about the solidity of frames and the spacing of frames. It works things into a tabulated setup as opposed to the plot that you were seeing on the previous slides, which is kind of nice. And it is another standard that we have referenced in the past. And then the Cranes and Derricks textbook by Shapiro and Shapiro also has shielding provisions. It provides some nice examples for different types of elements and different types of tower configurations. It's written kind of more with the crane in mind, but a tower crane mast is an unclad frame, a truss tower, and we have seen that it's reasonable to take a look at some of these provisions and think about them in terms of the building as a whole. Before we talk about the results of this particular case study, it is important to note that there isn't a lot of real prescribed language in terms of how exactly you should be doing this. The Code of Standard Practice makes the point that you need to consider it. It, by design, doesn't expound into that too much further. Even ASCE 37, while it is an ASCE standard, it's not a standard that's referenced by the International Building Code, and to our knowledge, is not really referenced in any codes aside from perhaps a local jurisdiction here and there. So it's a reference that is used in combination with engineering judgments, and it's probably one of the most detailed standards out there to help you through some of these challenges. But judgment is, of course, paramount in how you walk yourself through these sorts of challenges on projects. But at any rate, all the more reason why we like to pull in data from multiple standards. And when we ran each of these standards through the building, the generic building that I showed earlier in the presentation, these are the results that we got. These are wind loads as compared to the ASCE 37 non-shielded baseline. Taking the loads applied by the areas with no shielding based on the ASCE 37 wind velocities, and then adding in the additional shielding provisions from each of these standards, you can see what you get. So there is a reduction in most cases. There's a couple spots where we get no reduction. For ASCE 37, the east-west direction, it's just because we didn't have enough bays to even get to fourth and beyond bay to reduce the load. So it was just 100% in the east-west direction for ASCE 37. Bit of an anomaly that we got larger loads based on the petrochemical standard in the east-west direction. But if you average all of these, we got about 70% in the north-south direction, which was left-right on the page, and then 81% in the east-west direction, which was up-down on page. So more shielding in the direction where we are deeper. And what we did, or what we would do, I guess, in a case like this is think about the averaging of all of these and see if we feel like that's reasonable. And I don't think it would be unreasonable for a building like this to take a 25% reduction beyond the ASCE 37 baseline demands for shielding. So moving on to seismic demands during construction, and I won't dive into as much detail on this as the wind demands because I recognize that its degree of relevance is not the same for everyone listening in on the call today. But I did want to expand on it a bit, given how important it is to us to be keeping this in mind in areas where earthquakes are not all that uncommon. It's important to consider that many of the projects that we do here in California are not all that far from a fault, and that mid-size earthquakes are not all that uncommon. And it's possible that you may see one over the course of a 1 or 2 year construction project. So what I'd like to do is just dig into the AISC 37 provisions just a little bit here. So AISC 37 section 6.5 allows for up to an 80% reduction on your mapped spectral accelerations for the short period and the 1 second period. And in other words, you are allowed to take 0.2 times SS and 0.2 times S1. If you read the commentary in AISC 37, it is saying that you're allowed to take up to this 80% reduction. And that 80% reduction is intended to be somewhat akin to matching the risk level or the risk of collapse that AISC 7 implies for a building with a, say, 50-year design life to a 1 year construction duration. Now, every construction duration is different. Some may be longer, some may be shorter. The standard leaves it open to the user to calculate a different reduction that may be less than 80%. But speaking from personal experience, I know that many folks just take the 80% reduction. Something that is important to us and we're looking into for the next revision of AISC 37 is perhaps to add some additional information and input in the standard on how you could go about calculating your own reduction if you feel like the 80% is too aggressive. But I just wanted to make that note. Another important note and consideration is that the standard says that your site modifiers, FA and FV, need to be based on the unreduced accelerations. So that's an important distinction. So you're going to enter the two tables for FA and FV, not using 0.2 SS and 0.2 S1, but just plain old SS and S1. You're allowed to take an R factor, or response modification factor, of 2.5. The thinking behind that is a building that's in construction may not have its full lateral system engaged and available and ready to be used. What I mean by that is, for instance, a building with braced frames that relies on collectors in the floor plates to deliver loads to the brace frames and a diaphragm to get loads to the collectors. If all of those pieces are not fully connected with their permanent connections and fully intact, you may not be able to even develop the ductility in your ductile element, such as a buckling or strain brace frame, and you may get fracture in the connection beforehand. So the R factor of a highly ductile system in the R equals 6 to R equals 8 range is not necessarily achievable for a lateral system that's partially complete. And the 2.5 was determined as a reasonable parameter to use that captures some degree of ductility that you're still going to get in a steel structure, but keeping it pretty low. That's really important. I feel like I've seen instances where others have used a higher R factor, and the standard allows you to do it if you think that the system is intact, but you really need to think about that before you start taking that 1/8 reduction for an R of 8 on top of your 80% reduction on the seismic acceleration as well. And like I said before, this is not mandated by the Code of Standard Practice, but very much a consideration in certain seismic zones and situations. And of course, judgment and discretion is necessary. I just got a quick example here that I put together quickly to just run through the process. And I won't go into this in too much detail. The handouts are available, but you can see if we just look at the 0.2 second period process, you start with a 1.5 G acceleration in the Bay Area. This was done for Degenkolb's headquarters office in downtown San Francisco. You take that 80% reduction, 0.2 times the 1.5, that gives you 0.3. The site modification factor, FA, is 1.0, and again, that's based on an SS of 1.5. So you apply your FA, and then you get down to design by taking 2/3 of your SMS, and then you put the R factor through it to get down to a coefficient of 0.08. So you've reduced your seismic accelerations pretty substantially here. And that's why I underscore the importance of using judgments. And there are certainly cases in the past where we've taken that number and said, we don't feel comfortable going that low. We're going to stick with perhaps 0.2 instead of 0.08 as an example. So that example is here for you to take a look at in more detail in the handout. So that wraps up the seismic and wind discussion. So I would like to keep moving now on to topic number 2 and talk about structural complexity and tolerances. This is going to be framed primarily in terms of our experiences on the 181 Fremont project in San Francisco, which is a project that we did with the Herrick Corporation several years ago. Also benefited from some great interaction with the structural engineer of record on the project, Eric, and I do think that was really a fantastic collaboration that they were not, really contractually bound to participate in, but we kind of both set reasonable expectations, understood, the risk we were each assuming, and stayed, in our lanes with that, but were able to have access to their engineers to make sure we were understanding certain aspects of their design, and really just worked out as a great partnership. But a building like this, 800 feet tall, on a relatively small site, so relatively small floor plan. Floor plan was too small to accommodate a concrete core. The developer, the architect, did not want to give up the square footage that a concrete core would take up. So they went all steel with an external mega brace, 3 tiers of that, and a secondary moment frame system around the perimeter of the building to deliver loads to the panel points of the mega brace. And Herrick was very interested in understanding what this building was going to want to do as they erected each tier, relatively slender, with mega braces that would not get, quote unquote, noded out until you get to the top of their 20-story spans. And also varying sizes and types of columns, box columns with concrete fill, without concrete fill, also wide flanges in the interior. What was the building going to do as it got built? And we observed that this particular building, the behavior was really due to 2 primary factors of behavior. One, the building lean, which for the most part was due to the differences in elastic shortening of the columns as they received more and more self-weight of the building as the building got erected. And then also some building twist, which was a phenomenon that developed as more of the building got built and as those mega braces came into play and started influencing the behavior, wanting to turn the building into a rhombus as opposed to a square plan. And so some rotation associated with that, not to mention the irregularity of the floor plate as well. So it was important to really understand all of this and how it would influence erection and if there was any mitigating actions that the fabricator erector needed to take in advance to head this off. A quick chat about tolerances. And you have seen, if you attended the other webinars, you saw this tolerance figure in the middle of the screen in Tim's presentation in week 1. But AISC, the Code of Standard Practice, does establish an envelope for erection, and there's a number of different aspects to the tolerance provisions. The one I want to speak to is this global tolerance envelope that at the top of the building is 3 inches into the building and 2 inches out. And that was one of our focuses in putting together an erection plan for 181 Fremont. And we developed a tool, and I'll show you a screenshot of that on the next page, that took several sequences of the model of this building, basically 3 phases, up to the first mega brace panel point, and then up to the second one, and then up to the top. Took a look at what the building did as you started adding the different components of weight, being the steel self-weight, the concrete, some construction live load, a reasonable amount of superimposed dead load that we think might occur during the duration of construction, and then cladding as well. And we're able to take a look at the XYZ components or positions of each column at each floor level to see where they went as erection proceeded. And from that, we were able to actually take a look and plot out where we were at with respect to the AISC tolerance and determine if it would be reasonable to try to mitigate by perhaps setting some columns slightly out of plumb. And that's actually what Herrick did in certain instances on this project to keep the building on track to end up where they wanted it to end up at the end of erection. We did this with what we called a dashboard setup, which was really just a big spreadsheet interpolator. We considered other options. There's, of course, a very nice module in SAP 2000, which we've used as well in the past, where you can sequence your construction and take a look at the loads in each stage. But what was really needed for this project was a simple tool that could be adjusted by the erector to take a look at where they need to be at a given level. So this tool actually allowed for input of progress of steel, of concrete, of cladding, of expected superimposed live and dead loads, and plot coordinates in XYZ for each column with respect to the theoretical locations to help the erector understand why their surveys might be showing something off of the theoretical location, to help them mitigate conditions where they wanted to actually head off some of that, but also how it impacted grid lines for the future build out of the interiors. We came to an agreement to actually share this with the general contractor as well, and they used it for that purpose. A little side note, which isn't directly related to what I've just been talking about, but does relate to the structural complexity. On this particular project, and we've seen this on other projects as well, you've got a tight floor plate. You don't have a lot of room down at the base to really establish the entryway that you might be looking for into the lobby of your building. There's a desire to not have as many columns. So this building had mega trusses flanking the four sides of the building. You can see that on the left. And those mega trusses would be holding up about 40 stories of steel above before another transfer truss headed off the rest of the building up at the 40th floor. And so these trusses were very heavy elements. There were limits to how long the pieces could be for trucking, and also capacity of the crane to get them into place. And so these trusses needed to be stick-built on site in small workable pieces. So false work was needed to support those trusses and hold them at their cambered locations until Herrick could get them fully completed and welded off. And the question of where to shore to came up. And we were able to use the perimeter excavation shoring as a means to support our false work. You can see that in the photo. Those sloped columns are our false work. We needed to slope them to get us from the location of the trusses at the top, slightly offset at the base to get out to the perimeter excavation shoring. And we were able to do this and coordinate loads with the excavation subcontractor's engineer. And it worked out really nicely because the excavation shoring was very stout. It was a cutter sew mix wall with steel solder beams at 4 feet on center, very heavy beams. And so there was plenty to push to. And it kept columns, temporary columns, out of the concrete floor down below, which was really nice because I think the more we can avoid touch points and constraints between trades, the better. So the sloping, we ended up working out those forces, those lateral kicks that resulted by just having false work similarly sloped on the other side, created a pretty coherent and equilibrated system. Okay, moving on to our next topic, pushing height limits during construction. So there's a little bit of language in OSHA with respect to how far your erection can proceed above certain benchmark conditions in your site. Many of you, I'm sure, are familiar with this language. Quickly reviewing, this is out of section 19.6, 754. Structural stability shall be maintained at all times during the erection process. No surprises there. But then the next clause goes in to say that there shouldn't be more than 8 stories between the erection floor and the uppermost permanent floor, except where you're holding your structural integrity. Similarly, no more than 4 floors of unfinished bolting or welding above the foundation or uppermost permanently secured floor. And so both of these establish a maximum that you can extend with in essence your leading edge of erection above a more coherent degree of construction. And I think there can probably be some discussion as to permanent floor and permanently secured floor and what exactly that terminology is referring to. But I know on 181 Fremont we were thinking of 8 stories above concrete as being a proxy for this limitation. There was certainly a desire on that project and other projects to go higher than that. And it gets even more gray when you don't even have a lateral system to set your benchmark. And I'm going to go into that in a little bit further here and hopefully clarify some of what I was just referring to. This is almost somewhat outside of the OSHA provisions, but let's take a couple different types of lateral systems for buildings. On the left, we've got a BRB core building, so some buckling restrained braces oriented in 4 directions at the interior bay and serving as that backbone for the high rise. On the right, a mega brace system similar to 181 Fremont. And we have the terminology here on the screen related to the leading edge of erection for the BRB core, which I'm referring to as it's kind of the bare gravity steel, potentially extending above the installation of BRBs. And I'm not saying that's necessarily how a building like this would get built, but just for discussion purposes, we'll call that the leading edge. And then the introduction of a delay zone. And this is something that we have seen come up more with the more complex lateral systems. There's a desire from the SEOR to keep gravity loads out of the lateral resisting elements so that you don't bake gravity loads in as you're building the building and potentially reduce the amount of reserve capacity available to deal with wind and seismic. And perhaps a desire to either hold those braces out completely or have them attached but perhaps loosely bolted or maybe only bolted at the top or bottom so that they don't pick up gravity loads as more of the building's weight is added up above. Same goes for the mega brace system on the right, and we encountered this at 181 Fremont. Those particular mega braces were detailed such that they slid with respect to the intermediate floors they were passing through. And the intermediate floors provided some bracing to cut down on the unbraced length of the brace, but there was not a desire to actually transfer lateral loads into that brace at an intermediate story. The lateral loads were transferring in only at their nodes at top and bottom. And so for the 20 stories roughly that we encounter on 181, you've got 20 stories of erection without your primary lateral system in place. And how do you ensure that building stability and plumbness is held as you're erecting those floors? And so what I'd like to talk about here is some sources of where you can find temporary lateral support to help deal with high-rise structures such as these that have these unique lateral systems. We'll go through a couple examples. The first one I want to talk about is if you are lucky enough to have a secondary moment frame present, which we did at 181 Fremont, you can certainly try to rely on those. Now, even this secondary system, there were some provisions with respect to delaying certain connections. There was a concern that some Varenbiel truss action could develop if your moment frame was fully welded off and was actually trying to span some of the weight of the building out to the really stiff outer corner columns. A good compromise on that front was to leave, I believe it was the bottom flange of the moment frames at the corners or at the column connections unwelded until later, but we were able to still get fully welded moment frames for the 2 interior bays on each of the 4 sides of the building. And in the case of 181 Fremont, we looked at those lateral system elements on their own against wind and seismic loads from AISC 14 to see if there was enough strength and stiffness to accommodate those loads and also to accommodate the loads from the tower crane. We were able to get that to work in that particular case. So certainly keeping in mind these secondary systems, which need to be in place and present for a mega brace building, because you need something to deliver loads up and down to the panel points of the mega braces. See if you can take advantage of those to help you in the various stages of erection. Gravity connections are another place where you can seek some extra strength and stiffness. And I will say that we typically don't want to rely on this on its own as our only system because these connections are not detailed to be moment connections. However, if you're looking for a little extra help, there is an equation in the FEMA standard 355B, which does date back to 2000, that allows you to estimate the stiffness of a gravity connection, and that's based on actual tests that were performed, I believe, in the aftermath of the Northridge earthquake. And you can generate a spring constant that you can put into your model and then check to see how much moment those connections may actually want to resist when loads are applied to your model. And then from there, you can use first principles to take a look at, how much moment capacity you could actually generate from the bolts in your connections going into bearing, obviously considering the strength of the shear tab and the welds to the column as well. So that's another strategy that we have used in the past to try to help us out. Another approach that we have used is thinking about temporary connections of a brace element that could allow for some degree of slippage, but will then engage after that slip is taken up to hopefully preserve stability, but allow for some room in the meantime to allow for some gravity shortening to take place without snagging those bolts and in turn baking loads into the braces. So just a quick schematic here showing that you've got a bolted brace connection and thinking about a slotted hole so the brace can get bolted up. The slotted hole allows for some movement as the building gets loaded above. The top of that slot starts moving downward towards the bolt, or in reverse, the bolt is moving closer to the top of the slotted hole. Using calculations to determine the degree of shortening, the amount of shortening you would expect in a given story, and making sure that there's enough room in that slot to take up that movement, and then coming back and tightening off those bolts to slip critical, or perhaps welding the braces off once you've gotten past a reasonable amount of shortening in the building. It's a strategy that we have used. A quick clarification, it may not be completely clear in my graphic here, but the slots are going to be parallel to the longitudinal axis of the brace. Metal deck diaphragms, the diaphragm is certainly an important part of many lateral systems and can play a very important role in the lateral stability of your building. And so what I'm showing here is a bare metal deck diaphragm prior to getting any sort of concrete, and highlighting some of the considerations. The capacity of that deck is very much influenced by the connections. And you need to be mindful of what deck is being used and what the permanent connections are going to be, and whether those connections might be enough to get you enough temporary strength when the deck is bare and doesn't have concrete on it. Support attachments, being perhaps a welded stud or a spot weld, or a powder actuated fastener, or a screw, those side lap attachments, kind of shown in the dash within that blue shaded area, being a seam weld, a button punch, or another proprietary system. So digging into that a little bit further, we find these are interesting conversations that come up on a project. Using 181 Fremont as an example, we really needed that deck in relatively early so that we could send our loads, in particular the tower crane loads, which we'll get into a little bit later, out to the perimeter moment frame. The challenge, going down to the considerations that I'm showing down at the bottom of the slide, are multiple. Who's selecting the final deck configuration comes up. Sometimes the SEOR has indicated a minimum that they're requiring, but they're not all that concerned about it because the concrete's going to come in and really provide that diaphragm action at the end. And so the gauge of the deck is maybe not all that important to them, and they leave it up to the contractor. So finding out what gauge is actually going to be used on the project is not always as easy as just going into the structural drawings. Also important is who is the client for the decker? Who's the decker working for? Why that's an important point is depending on whether the decker is held by the steel erector or by the general contractor, can create different dynamics for how conversations are had with respect to when is deck getting laid down, how quickly can it get laid down after the erectors get out of the way, and is that going to be enough to give you the supports that you need. So some important points that you want to consider if you feel like that deck is going to be important and you're going to need it in place, you want to have those conversations relatively early with respect to how quickly can the deck get welded down, and that's likely going to be more than just wind tacking. Wind tacking is not going to allow you to develop anything close to the strength of the deck. And so it's really an expedited laying down of the deck, but also getting good connections in there. Is there an opportunity to perhaps consider a slightly heavier gauge if it helps out erection, but weighing the cost implications of that? Thinking about an alternate connection method, so either going to a more closely spaced connection. We see this especially with respect to the side lap connections, which can be pretty sensitive and can really swing the total capacity of the deck, depending on whether you're using a 24-inch spacing versus a 12-inch spacing, or maybe going to a top seam weld versus a button punch, or vice versa. Citing the capacity tables that you'll find in some of the decking literature to help you make those decisions can make a big difference. We have been in this situation in the past and probably have not always come to the table as early as we really would have liked to be able to help facilitate these discussions to benefit the erector. Okay, on to topic 4, erection aids and lifting lugs. Okay, so just to talk a little bit about terminology first, just in case there are folks that aren't clear. When I say an erection aid, for the purpose of this discussion, I'm talking about temporary connections that can allow for a column to be set and let go from the crane prior to completing the welded splice at the base of that column. And for a lifting lug, I'm talking about the extra steel that might be needed to provide the crane with a coherent point to connect to and to support the element, in this case a column, while it's on the hook. And those are the two sketches that you can see on the right. Why I felt like this was a worthwhile topic to bring into the presentation is because, especially for these all steel structures, the advent and the use of box columns, it seems like it's becoming a bit more prevalent. And many times these box column elements are obviously quite heavy. We have seen some on the order of 50 plus tons, and that's perhaps only over a few stories. When you start thinking about gusset plates and stiffeners, the wall thickness, they get quite heavy. Also, a splice for a box column that's 3 or 4 feet plan dimension, width and depth, could take days or even more than a week to weld off a complete joint penetration weld. You can see that happening in the picture on the left here. So setting the column on erection aids and taking it off the crane, it's more than just a couple hour exposure before splices get welded off. It could be days, if not weeks, before that happens, which really underscores the importance of a robust and designed, engineered erection aid to provide that support. And then the weights are directly related to the importance of a really close look for the design of your lifting lugs. So for those reasons, we wanted to dig into that a little bit further in today's discussion. Let's talk about erection aids first. And in digging into OSHA, you'll find that there is not a lot of guidance, at least that I am aware of, in terms of how you would design a temporary connection, which Guy will show, more zoomed into you on the next slide. So a temporary connection that can satisfy the different demands that we expect might be encountered while that erection aid is in service and prior to the joint being fully welded off. OSHA, many of you have seen, prescribes a 300-pound load located 18 inches eccentric from the extreme outer face of the column in each direction, which is a representation perhaps of a person, an ironworker, hanging off of the side, but perhaps capturing a little bit of incidental impact load as well built into that, but it's not a substantial load. Our standard of practice, especially when dealing with these heavy columns and especially in a high-rise situation, is to obviously be also thinking about wind, which the Code of Standard Practice requires, but also be thinking a little bit about seismic and also impact. And what we typically use when designing erection aids is generating wind demands in the same manner that we're doing for the global building, using the truss tower analogy and applying loads to the exposed surface area based on the AISC 37 demands. For seismic, we'll do the same. We will sometimes, like I mentioned briefly previously, go a little higher. 20% of weight has been a nice balancing point of capturing something more than that fully reduced reduction that includes the R factor in AISC 37. 20% of weights has worked well for us in the past and gives us a little bit more oomph to these designs in the event of a tumbler rolling through while these columns are at their most fragile sequence points, if you will. Impact, we've seen some of our clients like to consider this as well, and this can vary, but in this case, you're perhaps talking about a lateral point load applied to the top of the column, perhaps a kit, perhaps a little bit higher than that, depending on the sorts of actions you're expecting on the site at the time of setting your column. And taking these demands and running a typical code design with capacities generated per standard ASD or LRFD methods per the steel manual. When you're looking at a design like this, which in this case is a set of plate ears welded onto the columns above and below the splice, and then angles linking them through, and I should mention that this is a generic typical detail. You would not typically see this many bolts necessarily, and also not necessarily the 8 locations kind of on each side of each corner. But we're just using this figure as an example. You got to think about all the loads coming through this splice. So the blue arrows, vertical is your gravity load. You've got an overturning moment from this column cantilevering up. That's going to generate tension compression couple in your angles. And then, of course, you've got the shear that's also generated from those lateral loads. For a column like this, we'll typically advocate for bearing to take out the gravity load, either the root face being enough to for the PJP weld prep to take that bearing, or in cases where you're required to have a complete joint penetration welds, upsizing the backing bars a bit and having backing bars both above and below so that they can bear on each other and take the gravity load out of the equation for the purposes of designing your erection aid. Works really nicely. But then with the erection aid itself, it's not just taking the vertical tension compression couple through those bolts. You have to think about that shear transferring from the top of the splice to the bottom of the splice, akin to a little moment frame action, where the fixed supports I'm showing in that figure on the right are the connection to the face of the column, and then your columns of this moment frame, the horizontal elements, if you will, are that eccentricity to the siege, the line of action of your bolts, and then the vertical element, or the beam flipped on its side, if you will, would be the angle connecting your two fin plates together. And actually thinking about the moments that develop from the various eccentricities that are occurring, and making sure that you capture all of that in your connection design. Switching over to lifting lug design, quick water break. Thanks for that. So for lifting lug design, it's a slightly different approach. And it's a approach that considers a larger factor of safety in your design, recognizing the lack of redundancy when you have a large, heavy column hanging from a single point on a crane, sometimes swinging over a street or swinging over areas where there are workers below. It really necessitates a more, a higher degree of factor of safety. And what we typically do for these, the demand is the unfactored gravity weight of the element, requires a good attentive weight takeoff, and making sure that you've got the exact or close to the exact weight of the assembly, accounting for all the supplemental plates. In a case where the box might be receiving concrete, there may be consolidation rods or plates cutting through over the height of the column that may be adding weight as well. Making sure you have that captured when you're doing your calculation. And also keeping in mind that for a column that might be set at a slight angle, the erection aid is going to be oriented so that you're aligned with the CG of the elements as it rests on the hook on the crane. On the capacity side, we consider a factor of safety applied to the nominal capacity out of the steel spec. So what I mean by that is the capacity without applying a fee factor for LRFD or applying that omega factor for ASD, but then putting a factor of safety on that capacity. We went back into the literature. We've traditionally used a factor of safety of 5. In preparation of this presentation, I wanted to see if we could get something written that says that. And this is what we came up with in this table. There is a paper in Engineering Journal from 1991 by David Ricker that does call for a factor of safety of 5 in conditions such as this. But the ASME below the hook standard also digs into this further and goes into a little bit more detail and categorizes your conditions based on whether your magnitudes and variation in directions of loads are predictable or unpredictable. So our 5 falls in between category B and C, which is still towards the higher end of this. We will note that in certain areas we may use discretion to cut into that factor of safety a little bit, but our clients have generally felt very comfortable with the designs that using that factor of safety results in. I will note that when it comes to tripping, so the column being on the ground and getting pulled up to vertical before it gets hoisted, we will typically check tripping based on more of an approach akin to what we do for erection aids, recognizing that the column is still touching the ground, and especially if they're tripping in the strong way of your lug, that lug is more often than not going to work to trip the column also. A couple components to a typical lug design. Again, this is a generic detail. The holes that you see in the lug plate are allowing for consolidation rods to pass through for this particular box column. But there's a number of things that you need to check, just like you would any typical connection. Getting your lug aligned with the CG of the elements, that's number 1. Number 2, a bearing tear out check on the lifting eye. tension at your gross and net sections in that narrow appendage of the eye sticking out above the top of the column. That's number 3. Shear and flexure on your lug plate is number 4. 5 and 6 are the ones that we, more often than not, will run into some issues. That's the weld to the box wall and the localized effects on the box wall themselves. The question of what you're considering for fixity of that lug plate. That lug plate's going to be very stiff with respect to the more flexible weak way behavior of the box wall. So you could argue that you're not going to get a lot of fixed end moment in that lug plate because you're just going to get some rotation in the box wall. That can be a little hard to quantify, and even if we feel pretty strongly that's the behavior that's going to occur, sometimes the box column wall thicknesses get pretty thin if that concrete is going to come in later, and so it can be very sensitive. You need to be really careful to make sure that the weld that you're using to get loads out of your lug into the box wall can even be developed by the box wall depending on its thickness, and make sure that the box wall can get loads spread into the element appropriately. We'll sometimes do little models to take a look at what sort of moment you actually build up. If you consider a certain amount of box wall getting engaged, we'll sometimes actually go to finite element analysis to do this. But it's just something to really remain mindful of. Okay, and now digging into the last section of the presentation, doing a quick time check, and I think we're still doing okay here, a little bit on tower cranes. Those that aren't familiar with tower cranes, I'm sure you've seen them on building projects around large cities in particular, but everywhere these are widely used. They will either be cantilevered from a base foundation, typically up to around 200 feet, maybe a little bit more than that. They can cantilever, but anything higher than that, you're going to start introducing tie-ins. And tie-in is typically a 3-strut arrangement that collars around the mast of the crane and ties back to the building. The crane tie-ins and the loads that are applied to the building are typically supplied by the crane manufacturer or the representative supplier of that. But then once whatever receives those loads ends up falling to a different engineer. In our case, we have done that as part of our work for the steel erector. Sometimes we get engaged directly by the general contractor to do that work. A couple pictures of tower cranes that we've encountered. 250 Howard Street in San Francisco was not a project that we did the erection engineering on, but we did do the crane for the general contractor, and then 181 Fremont down at the bottom as well there in the second picture. A little bit of a pet peeve of mine, I think, is there are, much like a lot of this other work we've been talking about today, the supported tower cranes is not all that covered specifically in the code. There's a lot that's left to judgment. There are some spots that I think really deserve more clarification, and you really just need to be careful and understand what's happening and how this thing is behaving when you're putting together a plan to support a tower crane, either at foundation level or at tie-in. In particular, the demands. The simplest question, are those demands at ASD or LRFD level? Not every crane supplier clearly documents that. A lot of these demands are generated from an overseas code, especially the cranes that are built by companies in Europe and elsewhere. And one of the things that's personally bothered me is in some cases I've seen those demands really not change all that much over the years, even though our ASCE code went from a transition where wind load previously was supplied at ASC level and then factored by 1.6 to LRFD to now being a strength level load that then gets reduced if you want to get down to serviceability. So you could imagine that the same crane entering a building either prior to that code switch or after, there could be something left out somewhere where one of those two situations is not getting the factored demands right. Make sure you ask. When we're not sure, we assume they're coming in at ASD level to be able to sleep at night and feel like we've got, at worst, a conservative approach. Stiffness requirements are also really important to consider. And in particular, that comes into play when a crane tie-in is coming in at mid-height of a story. You could put in a column that takes those tie-in loads and spans them to the floors above and below. But if that column, even though it works for strength, if it's not stiff enough with respect to the relative stiffness of the crane mast, you could imagine that the crane mast might be forced to send loads to other places farther than is really intended. So asking about stiffness requirements from the crane supplier and see if they have anything. We have noticed or seen in the past that the L over 500 limit, in other words, limiting the deflection from one tying point to the next, being akin to that height between those 2 points over 500. We've used that. We've seen that work in the past. I'm not saying that that's something that should be used everywhere. It's a very case-by-case thing, but that's just one number I wanted to cite as one that we have seen. Another condition to consider is who is designing the bolt that's tying to that's connecting the tie-in shoe to the building. And sometimes they're covered and supplied by the crane folks. Other times they're left to the steel erector. I had one case where I ran the demand supplied by the crane manufacturer through the largest bolts that we could get that would fit in the holes by the supplied shoe, and the design wasn't working. So a bit of a disconnect there. We were able to negotiate some super high strengths and get around it, I believe, without having to ream larger holes in the shoes. But it was a kind of a curious moment. We don't always get asked to check those bolts, but something to remain mindful of. Cladding limitations, and this is not just on the engineer, but really on everyone involved in the project, and the GC in particular, and their logistics planning. Our tie-ins, can they be aligned with the floor levels, or are there cladding constraints that would mess that up? So if the cladder really can only allow for some leave-outs in the mid-height windows and staying away from the mullions or the bands at floor levels, that might push the tie-ins to a different location, or a worse location that might be desirable from an engineering standpoint. And then delayed lateral systems, like we've talked about previously. If that building doesn't have a robust lateral system in place, where are the loads going to get sent while the building is still under construction? Just going to share very quickly a couple examples of what we have done in the past for this. The first I call the load spreading approach. We dealt with this on 181 Fremont, where you had no mega braces in place. You just had perimeter moment frame, 2 of the 4 bays on each side. We're receiving crane loads on the order of 100 kips or more. Where do you send that load? We spread the load above and below to the floors up above and below, but then actually also braced an additional floor above and an additional floor below to get loads to 4 diaphragms to be able to keep those loads small enough such that the deck could get the loads out to the moment frame. It's a pretty large number of floors, and it created challenges for sure, because there weren't more than a couple floors of deck above even available. The building hadn't been built yet. Your crane is at leading edge of erection, so the 2 floors above was really as far as we could go. And of course, we were coming up at every jump, just the challenge of the deckers being able to get that deck welded down in time. It was a huge obstacle. We don't deny that at all, but on this project with no concrete core, a pretty sensitive, flexible building, we explained it early on that this was going to be necessary, and everyone bought into it as really the best way to go. The perimeter approach, again, this was used at 181 Fremont. It was a different approach because at one tie-in level, there was a very crowded mechanical floor with a lot of pieces that needed to be set as the building got erected because they wouldn't be able to get in afterwards. And so we had no option to do our typical load spreading approach. And so we had to keep our solution to the perimeter of the building. And so this was a bit more of a brute force method. Some very large built up box column actually, no, I take that back. I think we were using some HSS 20 by 20s with thick wall thicknesses to take loads from a large wide flange header, span the loads horizontally, to the vertical tubes, and then those went up and down to the transfer girders that fortunately were in place at this particular location to take these large loads, and then just distribute them into the moment frames from there. One particular challenge here was that transfer level was slated to get another 20 floors above, and it was going to deflect as the building got built. Our tie-in could not constrain that deflection. Otherwise, it was going to be a big issue to cut that out later and let the deflection happen at a later date. So the top, we needed a connection that allowed for vertical slippage, and it worked. But I will say that we, in hindsight, probably could have stiffened the inside of the top of that box column or that HSS tube further to prevent some distortion as that box was getting twisted by the crane tie-in loads. It made a lot of noise as it deformed with respect to this little hat piece that we had on the top. It was audible. It definitely made some folks a little skittish out on site. We needed to get out there and talk to the team and to OSHA to confirm that we had run all the checks and that it was fine. But in hindsight, we would have probably wanted to stiffen that a bit more. Minimal removal approach. This was for the 250 Howard Tower. This was a concrete core building, but I think the points are still holding true, even if it was an all steel building. In this case, we were working for the GC, and they recognized that removal of temporary steel can be challenging sometimes, especially if your erector is off the job, but the crane is still in service. They wanted to limit the amount of steel that had to get removed. It's a little hard to see in this picture, but what we did here was we strutted diagonally downward to the location of the tie-in, pulled those loads back into the closest floor above, strengthened all of those permanent beams to take the vertical kick resulting from the component of this diagonal element to keep within required stiffness considerations. We needed to make sure that the SUR knew we were strengthening these beams and that they probably wouldn't need to be cambered like the typical beams so that you didn't get a potential bump in the floor. These stiff beams would not deflect enough to take camber out once they get loaded with concrete. And at the end, it was just those diagonal elements that needed to get removed, and the extra steel in plane with the floor just ended up staying in place. So that wraps up the tower crane section and gets to the ends of my presentation. I just wanted to share a couple additional final thoughts. It's obvious that the erection engineer can play a very important role on a project, especially a challenging and complex high-rise structures like the ones we cited here in the presentation today. And the fact, and rightfully so, as buildings get more complicated, there is more gray area as far as who's responsible for these interim stages of construction. For many reasons, the SEOR is not taking on those responsibilities. It is unfortunately putting more responsibility on the erector and their engineer to deal with these. And it's important to remain mindful of that. A lot of creativity goes into a lot of these schemes, as well as an understanding of behavior being extremely important. You will find that you will gain a very deep understanding and need to gain a very deep understanding of some of these buildings and how they behave to be able to head off some of the issues with respect to tolerances and stiffness and tower cranes, because no other engineer is most likely looking at those things before you get involved on the project. And again, just repeating the points that I made about AISC 37 previously, again, keeping in mind that it is a document, that it's a published standard by AISC. It is typically not adopted by any code. It is there as a guide and probably the best one available to deal with loads on structures during construction. But it is subject to some judgments and judgment-related considerations by the user. It needs to be used in that manner. As just kind of a final thing, I will say, I have gone through each of these topics very quickly. They are not the only topics that are important to dealing with high-rise structures. I am probably leaving you with plenty of questions, and I think there'll be some time here shortly to take some questions. And and I believe also a process to answer unanswered ones after the fact. But my contact information is here, and you are more than welcome to reach out to me directly by phone or email. If you would like any additional input on any parts of the presentation today, I enjoy that. It's for the betterment of the industry, really, in tackling these challenging projects. There's going to be more of these as we go along. And as I wrap up, I'll just leave you with a nice view of San Francisco Bay from one of the upper floors of 181 Fremont. I hate to say that the skies don't look like this today, unfortunately. My thoughts are with everyone who's dealing with the fires and other natural disasters around here and other places. But this is one of the best parts, I think, of going through a project like this. With that, I will pause, and I think I will toss it back to Nate. So thank you very much.
All right. Thanks a lot, Tim, for that presentation. So we do have quite a few questions that have come in, and we'll get to those here in a moment. But first, we will put forth a couple of poll questions for the audience, as we've done in the last couple weeks. And so here, the audience should see that first poll question on their screens. This is a fill in the blank. The computed wind base shear on a specific steel high-rise structure is blank higher during construction than after construction is completed. Is that A, never, B, sometimes, or C, always? Again, that statement, the computed wind base shear on a specific steel high-rise structure is blank higher during construction than after construction is completed. Give people a chance to get those answers in. We'll be closing in 5 seconds here. All right, let's go to the results. All right, Tim, so some interesting responses here. We have about 16% saying A, never, 77% think the answer is B, sometimes, and about 6% thinks that the correct answer is always. What was the answer you were looking for?
So the answer there is B, as the majority of the audience got, so good job. And that goes back to the points I was making earlier about how an unclad structure, depending on the configuration of columns and beams, the surface areas available, could in some cases generate more wind load than a structure that is clad and blocking the wind load from getting into those interior elements. This actually also goes back for those of you that attended Tim Duke's presentation a couple weeks ago. He was showing some examples of wind limitations on wind speeds for certain stages of certain erection procedures. This really, it goes back to that. Elements with fairly large surface areas can generate a lot of wind load, and you really need to be aware of that on both an element level and a global level as well.
All right, let's see how people do on the second poll question here. So this question is as follows. Which of the following can provide temporary lateral support during steel erection? A, temporary bolted connections on braces. B, partial fixity provided by bolted gravity connections. C, early or expected installation of metal deck diaphragms. Or D, all of the above. Again, which of the following can provide temporary lateral support during steel erection? Give you another 5 seconds or so to get your answers in before we close the poll. All right, let's go to the results. All right, Tim, it looks like it was nearly everybody who thought that D was the correct answer. Did they get that one right?
They did. We nailed this one. Yeah, so these are all examples that I cited in the presentation today. They are certainly not the only ones. There are all sorts of ways that you can get extra load. Definitely a creative aspect of tackling this particular challenge. But that is right. All three of these examples can potentially provide some support for your building while it's getting erected.
All right, so let's get to some of these audience questions. The first one will bring us back to slide 18. Question is, when looking at this floor plan and the wind is perpendicular to the spans of the infill beams, do you consider wind on every infill beam or just on the column line beams and columns?
So for the, make sure I answer this clearly. So if the wind is going left-right on plan, the current documented processes for these, absent a really clear, shielding provision, would imply that for the left-right wind loads, you would be applying loads to any vertical face that you encounter as you go through the building. So in the left-right direction, you've got, 3, 6, 9, 12, 15, 18 or so rows of beams that you would, if you're using AISC 37, for instance, you could take a 15% wind reduction on rows 4 through 18. But the idea is that you're applying loads to all beams, you're applying loads to vertical faces of columns, and in that case, for the left-right wind load, you would be applying the load to just one face of the column, the one that's head-on with the wind. If you're going in the other direction, those the beams aside the girders are going to be facing your wind load. So there's 3 rows of girders in the up-down direction on the screen. The beams that are parallel to your wind load would not really be picking up any wind load in that case. One other quick nuance for that, if you're thinking about a wide flange column and you're thinking about a wind load that is blowing in the strong axis direction of the column, we would take wind load on both the front flange and the majority of the back flange because both of those are, in essence, exposed. A lot of ways you can generate a lot of load. I definitely don't deny that. That's part of the reason why the shielding discussion is so prevalent and people are interested in it, is because it's hard to make the statement that you're going to get the same wind demands at the back face of this left-right wind, the back face of the building versus the front face with only a 15% reduction. It could likely be very much more than that.
All right. So keeping with that discussion about shielding, let's go to slide 24. The question asker notes that there's such a big discrepancy between these values. Do you have any guidance in how to select which standard to use in varying situations?
And I wish I had a great answer to that. You could make a strong case for instance, in these examples, Design Guide 10 did give a fair bit lower results than a lot of the other standards. That could be a clear reason to potentially discount, the results of that one. You may find as you read into the provisions for each of these standards that some pertain more to certain buildings and less to others. AISC 37 is written pretty generically such that, the intent is that you could apply to pretty much any building. The offshoot, unfortunately, is you don't get a huge reduction there, versus you could be getting a more aggressive, reduction out of some of the other standards. But, like the petrochemical standard or the cranes and derricks standard, we're maybe going a little bit more out on a limb on the applicability of those standards. So, this is, like many other things, the spot where judgment comes into play, using discretion. having a conversation with your clients as well. You could even, get into, looking at the weather history, in a given area over the years, although, much like Seismic, it's kind of hard to argue that that's a great approach when, there's still a possibility that a given event could occur at any time, but that weighs into it as well. So, it's the same question that we come up on every project, and really our best answer has been, let's try to feed in as much data from respected references as we can and try to just level the playing field a bit and, and temper those really aggressive ones, but help us out a little bit more than the ones that are pretty non-aggressive.
All right. So you mentioned having discussions with your client in these types of situations. So it brings up the next question. Do you normally in your practice work for the owner or the erector?
From a maybe stepping back for a second to Degenkolb's overall construction engineering services, which includes erection engineering, but also goes into some of the other things that Nate mentioned in my introduction. We will contract with many different types of parties, that is more often than not for erection engineering services. I mean, we're pretty much always contracted with the erector or the fabricator erector if it's the same party. We occasionally, we also work for general contractors. If it's just a tower crane, more often than not, we see that work happen with the general contractor, and then we just need to make sure we're coordinating with the erector as well. There are certain instances where we have works for the owner also, although that's more rare. And then, from a bigger picture at Degenkolb, I mean, we will sometimes do work for directly this work for architects or developers or others, but that's kind of beyond the purview of this presentation today. So, but in summary, we're almost exclusively doing the steel erection engineering for the steel erector, and then sometimes we're working for the general contractor or in small amounts of cases for the owner.
All right. Well, we're a bit past time here, so thank you for those responses there, Tim. And we had quite a few other great questions we weren't able to get to during this live session. So I do want to just mention again that we did receive those questions, and we'll work with Tim in the coming week to provide some responses to those folks who we did not get to by